So hi and hello there, welcome to the new video of the course, and in this particular video we are going to understand the concept of zero temperature drift in case of JFET or junction field-effect transistor. But before coming to this particular concept, I would like to revise the concept that we had seen in our previous courses. So if you could remember, when we were dealing with conductors and even in case of semiconductors, I told you that if the surrounding temperature of the semiconductor or the conductor increases, then what is going to happen? Whatever the atom that is present, inside that particular atom we have electrons, right? So that particular electrons will get ejected as it will gain certain energy due to heat, right? This is what we had learned, and then that particular electron will take part in the conduction. Okay, so this is what we had studied in our previous few videos, if you could remember. Okay, but things literally changes when we are dealing with JFETs. That means what is going to happen when we are going to perform certain operation with the JFET, and if the surrounding temperature of the JFET increases suddenly, then things really change, and this is what we are going to see in this particular session. Okay, so you can clearly see over here I had clearly mentioned that when the surrounding temperature of the JFET increases, two phenomena takes place at the same time. That is what? Increase in drain current ID. So this is the very first condition, and I know you are very much well acquainted with this particular thing, that how exactly it is going to increase. And secondly, decrease in current ID. Okay, so these are the two opposite cases, but they happen simultaneously. That means they happen at the same time. So this is what we are going to see in this particular session, that how exactly these two phenomena takes place at the same time. Okay, so for that what we need to do is that, let me proceed further. Alright, so now what we are going to do, we are going to assume certain cases, and then we will try to understand that how exactly things work internally in case of JFET. Okay, so the very first case that we are taking is that we are assuming that JFET is operating at around room temperature, which is equivalent to 25 degrees Celsius, right? So we are assuming that we are operating JFET at room temperature that is equivalent to 25 degrees Celsius, right? So let me just write over here. Okay, and obviously we had connected this particular JFET, I mean the drain terminal of JFET, to plus VCC. So this is your plus VCC, this is ground. Okay, this is ground, and this is lattice atom. Now I'm not going to explain that what exactly is lattice atom, because this is the concept of physics. So I believe that you are very much familiar with this particular concept of what is lattice atom, and even if you are not that much familiar with this particular concept, then just try to think that this is your n channel, and in n channel obviously there are few atoms that are present, right? So this is that particular atom. Okay, now I'm not explaining what exactly is the lattice atom. Okay, so just try to understand, or just try to believe that lattice atom is nothing but a normal atom which is just present in this particular n channel. Okay, great. Now we will try to understand that how exactly things work. Okay, when we are actually providing positive voltage to the drain terminal, and then we are grounding the source. Obviously the gate would be provided with the negative voltage, okay, which is not less than Vp. Okay, alright, so let's assume there are around 100 electrons over here. Okay, so whenever we are providing certain voltage to the drain terminal, so what is going to happen? So this particular 100 electrons will move over here in this particular direction. Okay, so it will move in this particular direction from bottom to top, or rather from down to top, right? But in this particular process, what is going to happen? Out of this 100 electrons, maybe 90 electrons will move very quickly. So 90 electrons, they may move very quickly. Okay, but rest of the 10 electrons, what is going to happen with them? So this particular 10 electrons would be getting obstructed by this particular lattice atom. Okay, this particular 10 atoms would be getting this particular 10 electrons would be getting obstructed by this particular lattice atom. So like this particular lattice atom, it won't hold that particular electrons for the longer time. Rather, what is going to happen? It will just try to decrease the speed of electrons. I hope you are getting this particular point. So we will take just a random number. I know the internal structure of JFET, it would be in micrometers, but for our understanding purpose, we will consider the speed of that particular electron as 10 meter per second. I know, again I am repeating this particular part, that the internal structure of JFET, it would be in micrometers, but just for our understanding purpose, I am considering this particular case in meter per second. So let's assume the speed of this particular electrons, all of these 100 electrons, it is 10 meter per second, right? So this particular 90 electrons which reached at this particular drain terminal, or rather which reached very quickly to the drain terminal. So this particular 90 electrons had the speed of 10 meter per second till the end, right? But this particular 10 electrons which were which were being obstructed by this particular lattice atom, so when it reached at this particular point, maybe this particular 10 electrons had speed of around 7 meter per second, okay, when it reached the drain terminal. So you can clearly see like at the end all of the 100 electrons, they are able to reach at this particular drain terminal. So basically in this particular scenario, there isn't any increase or decrease in the current. I hope you are getting this particular point. Okay, I hope you are getting this particular point. So during normal operation, or rather during normal condition, like when we are operating JFET in at around room temperature, which is equivalent to 25 degrees Celsius, so majority of the electrons, they are able to move from source to drain, and therefore the current is it won't increase, or rather it won't decrease as well. It will remain as it is. Okay, and then it totally depends on this particular voltage VCC. If we are increasing it, so obviously the current will increase, and after some time it would be constant. So if you could remember the drain source characteristic, right? Okay, I don't want to go into that particular point. What I want to convey, or rather what I want to tell to you all guys, is this particular part, that is lattice atom. So basically what is the role of lattice atom over here? The role of lattice atom over here is to decrease the speed or to obstruct the electron. Okay, so let me write over here, just a second. This lattice atom obstructs, or rather by obstructing it is decreasing the speed of electrons which are moving from source to drain. Okay, which are moving from or rather which are traveling from source to drain. Okay, source to drain. So this is what the function of lattice atom is, to drain. Okay, great. On contrary, you can also try to assume this particular situation as football, as like this particular whole of the JFET, it is like a football ground. This particular lattice atom is like a defender. So let me write over here. I know most of you all guys watch football. Okay, so you can try to relate this particular concept with that particular game, right? So this particular lattice atom, they are like defenders, okay, which are standing still in their respective position. So you can clearly see they're standing still. Okay, and this particular electron, they will act like your football, or other ball, whatever you say. Okay, and what you are doing, you are kicking the ball from this particular end. You are kicking the ball. Let me take different color. Yeah. Alright. So what you are doing, you are kicking the ball from this particular end. That means from source, and then you want that this particular ball should reach over here towards your drain. So your drain is like your goal. Okay. But this particular defenders, they will try to obstruct the ball, or rather they will try to decrease this velocity of the ball, so that this particular ball should not reach to your goal, or rather this particular ball should not reach to your drain terminal. Okay, I hope you are trying to relate that particular game, that means football, with this particular concept. I hope you are able to do that. Great, fabulous. Now let me move further. Alright, so now we are in this particular scenario to understand that how exactly things work when the temperature increases. So let me write over here. When temperature increases, I mean the surrounding temperature of JFET increases. When the surrounding temperature of the JFET, of JFET increases, so you can clearly see what is going to happen. This particular lattice atom, they will gain certain energy, and by gaining certain energy, they will try to vibrate with respect to their position. What I mean to say is that, see, this was the position of this particular lattice atom. So you can clearly see this was the position of this particular lattice atom. As soon as it gained energy, so it will try to vibrate, and due to vibration, it will look something like that. Okay, I hope you are getting this particular point. So it's like, at room temperature this particular lattice atom will stay still, or rather it will stay in its respective position, but as soon as it gains certain energy, so they will try to vibrate in this particular direction, or rather in x direction. You can clearly see negative x, positive x, negative x, positive x. So they will try to vibrate in this particular direction. I hope you are getting this particular point. Again, I am repeating, as soon as the surrounding temperature of the JFET increases, this particular lattice atom will gain certain energy, and due to this particular thing, what is going to happen? They will try to vibrate. Okay, they will try to vibrate in the x direction, positive x, negative x. Okay, let me write this particular point. So this is the second point. The lattice atom, just a second, the lattice atom start to gain certain energy, and start to vibrate, okay, and you can clearly see, due to vibration, it will try to obstruct many electrons. I hope you are getting this particular point. So these are the electrons which are moving from source to drain. So let me write over here. So if there are 100 electrons, okay, they are moving in this particular direction. So due to the vibration of this particular lattice atom, out of these 100 electrons, it might happen that only maybe 50 electrons reach over here. Ideally, practically all the 100 electrons will reach over here, but the speed would be totally different. 50 electrons will reach at the speed of 10 meter per second. Again, I am considering the same speed. So this particular 50 electron, they will reach very quickly at the speed of 10 meter per second. So basically, they won't be able to this particular lattice atom won't be able to decrease the speed of this particular electrons, but out of this particular 100 electrons, there are 50 electrons which will reach at this particular drain terminal at a speed of around maybe 6 to maybe I'll consider 5 meter per second. I hope you are getting this particular point. See, again I am repeating what all things we had studied. So let me come to this particular point. So over here you can clearly see, out of this 100 electrons, 90 electrons were reaching to the drain terminal quickly, right? And the 10 electrons, they were reaching but at the slower rate. Okay, so eventually you can see a decrease in the drain current, but that is negligible. This 7 meter per second, there isn't any such huge change. But when you try to compare this particular case with this one, you can clearly see 50 electrons, they reach very quickly at the speed of 10 meter per second, whereas the rest 50 electrons, they are traveling at the speed of 5 meter per second. So you can clearly see this particular number, it is getting multiplied by 5. I hope you are getting this particular point. So basically, due to this particular reason, what is going to happen? Eventually the current is going to decrease. Why? Because the velocity of the electrons decreases. So let me write over here this particular point. Due to this vibration of lattice atom, or rather I will write it in shortcut, due to this vibration, majority of the electrons will travel at very slower rate, will move, or rather it will travel at very slower rate. That means what is happening over here is that the velocity of the electrons is decreasing. So let me write over here, velocity of electron decreases. Okay, velocity of the electron decreases, and due to this, what is going to happen? Just a second. As the velocity of the electron decreases, so that means what? The current also decreases. I hope you are getting this particular point. So let me write over here, as the velocity of the electron decreases, decreases. Okay, so eventually the current ID also decreases. The current ID also, also just a second, also decreases. I hope you are able to understand this particular entire concept. Again, we will repeat what all things we had studied till now. When the surrounding temperature of the JFET increases, the lattice atom gains certain energy and start to vibrate. So you can clearly see this particular part. They had gained certain energy, okay, and that particular energy was in form of heat. So that particular heat energy they converted into physical energy as they are moving at certain point. So you can clearly see they are vibrating at certain point, okay, at certain axis, right? So due to this vibration, majority of the electrons will travel at a slower rate. So you can clearly see, since they are vibrating, so whatever the electrons that are moving from source to drain, so that particular electrons, or rather the velocity of that particular electron decreases, and since the velocity of that particular electron decreases, that means that particular electron will travel at very slower rate. So what we can say is that our current ID is decreasing due to this particular entire concept. Okay, I hope you are able to understand this particular part. Now what we are going to do, we are going to see this particular concept with the help of certain animation. So let me just show you that particular animation, just a second. Alright, so this is that particular animation. So let me run this particular animation, just a second. Alright, so you can clearly see during normal condition, this particular electron, they are moving from source to drain. Okay, just a second, yeah. And due to increase in temperature, see what is going to happen. See this particular crystal atom, they are vibrating at certain axis, and due to this particular vibration, the velocity of the electron decreases, and thus very few electrons would be able to move to the drain terminal with the same or with the constant velocity. Rather, majority of the electrons their velocity decreases. I hope you are able to imagine all of these things. Okay, so now what we will do, now that we had understood this particular concept of how exactly the drain current ID decreases as we are increasing the temperature, now we will focus on the second concept, that is this one, that is how exactly the drain current increases when we are actually decreasing the when the surrounding temperature of the JFET increases. So this is what we are going to see. Okay, so we had completed this particular part. Now we need to focus on this particular part, increase in current ID when we are actually operating JFET at around higher temperature, maybe temperature greater than room temperature, which is around 32 degrees Celsius, right? So this is what we are going to see. So let me move to that particular page. Studied, or rather we had seen how exactly the drain current decreases with increase in the temperature, okay, with increase in the surrounding temperature of JFET. So now we will focus on how exactly the drain current increases with the increase in the surrounding temperature of JFET. Okay, so for that I had taken the same image as you can clearly see over here, but the thing is that I had intentionally shown the depletion layer quite wider because there is one reason for it. I want to explain you certain things over here. Okay, alright, so we all know depletion layer forms because of electrons and holes. Okay, we all know this particular thing. Depletion layer is nothing but it's a kind of a layer where at one end you will get electrons and at the other end you will get holes, right? So basically depletion layer, it is made up of electrons and holes, right? Let me write over here, depletion layer, or rather depletion region, depletion layer or region is made up of holes and electron, right? Is made up of holes and electrons, right? Holes and electrons. This is the very first point. Okay, so what is going to happen as the temperature increases? So whatever the electrons that are present in the depletion layer, what is going to happen? They will be getting ejected out of this particular depletion layer. Okay, so let me write over here, this particular electron which is taking part in the formation of depletion layer, they will eject out of this particular depletion layer, and then they will take part in the conduction. I hope you are getting this particular point. And then they will take part in the conduction. So let me write over here. So the electrons which were taking part, So the electrons which were taking part in the conduction, taking part in the formation of the depletion layer or region, in the formation of the depletion layer, in the formation of the in the formation of the depletion region or layer, whatever you can say. Now what is going to happen as the temperature increases? So this particular electron, okay, so but as the temperature increases, this electron ejects out of the depletion layer. This electron ejects out of the depletion layer, or depletion region, and it takes part in conduction. Okay, thus you can clearly see, if these particular electrons which are present in this particular depletion layer, since they are ejecting out of this particular depletion layer and they are moving towards the n channel, right? So you can clearly see the depletion layer will decrease, or rather this particular junction barrier will decrease. Depletion layer in some books you will get this particular term as junction barrier. Okay, so it's one and the same. You don't worry about this particular point. So what exactly happens is that, thus, so let me write over here, thus the junction barrier or depletion layer, junction barrier or depletion layer or depletion region decreases, and n channel width, n channel, that means this is your n channel, right? If you could remember, this we had already seen, right? So the n channel width, or rather n channel region increases, and thus the drain current ID increases. Just a second. Thus the drain current ID increases. Okay, I hope now you are in this particular situation to understand what exactly happens when the surrounding temperature of the JFET increases. Okay, again we will repeat this particular point. When the surrounding temperature of the JFET increases, what is going to happen? The depletion layer, it is made up of holes and electrons. So the electrons which were taking part in the formation of the depletion layer, but as the temperature increases, this particular electron ejects out of this particular depletion layer and it takes part in conduction. So you can clearly see, I had clearly mentioned this particular thing over here. So this particular electron, it will be ejecting itself, okay, out of this particular depletion layer, and then it will be taking part in the conduction. So you can clearly see that since it is taking part in the conduction, so what is going to happen now? So due to this particular reason, now this particular depletion layer will decrease. So let me just show it over here. So this particular depletion layer or depletion region, it will decrease. Okay, so this particular depletion layer will decrease. So let me just write over here D1, D2, D1, just a second. So this is your D1 and this is your D2. Let me write over here D1 and D2. So D1 is depletion layer, depletion region before depletion region in the depletion region at room temperature at 25 degrees Celsius. I will write room temperature, and this is your depletion region D2. Okay, as temperature increases. Okay, and I know in many of the books and lots of the videos which are being posted on YouTube, there you will get only this explanation that as the temperature increases, the depletion layer decreases, but no one has explained this particular concept in this detailed way. Okay, so I'm the only one guy on the YouTube, okay, or rather you will say in the entire internet, that I had explained this particular concept in the detailed way. What exactly is the zero drift concept. Okay, again we will revise all of the things that we had studied till now. Alright, so as I started this particular session, I told you that when the surrounding temperature of the JFET increases, two phenomena takes place at the very at the very same time, that is simultaneously, that is increase in drain current ID and decrease in drain current ID. Okay, so during normal condition this particular JFET will behave absolutely fine. That means we won't see any change in the current. The current will be the current will flow as it is, right? We'll hardly see any change. But as soon as the temperature increases, this particular lattice atom, which you can clearly see over here, they start to vibrate. Okay, they start to vibrate, and due to this particular vibration, what is going to happen? Due to this particular vibration, the velocity of the electron decreases, and as the velocity of the electron decreases, so eventually the ID or the drain current ID also decreases, right? This is what we had seen. And at the same time, as the velocity of the electron is decreasing due to the vibration of lattice atom, but at the same time the another phenomena is also happening, that is this one. So whatever the electrons that are taking part in the formation of the depletion layer, they will eject out of this particular depletion layer, and then they will take part in the conduction. Okay, take part in the conduction. That means what? Eventually your ID increases. I hope you're getting this particular point. That means your depletion layer also decreases. So these are the few of the things that is happening simultaneously. So let me write over here, as the temperature increases. So this is the conclusion. So let me just write over here with the red color. As the temperature or rather as the surrounding temperature of the JFET increases, just a second, as the surrounding temperature of JFET increases, current ID decreases, drain current ID decreases due to the vibration of lattice atom, due to the vibration of lattice atoms. Okay, and experimentally it has been seen that it decreases by 0.7%. okay, so just a second, let me write over here. So the change in ID, it is equivalent to 0.7% of ID. That means what? So whatever the current ID that was flowing over here, so this is the ID, whatever the current ID that was flowing in the normal condition, right? Whatever the current ID that was flowing in the normal condition, so this particular current decreases by 0.7% when the temperature is getting increased. I hope you are getting this particular point. So that's why I had written it in this way, that is ID, it is equivalent to 0.7% of the ID, and this particular ID is when your JFET is operating at room temperature, that is 25 degrees Celsius, right? Okay, so let me erase this particular part. Just a second, let me erase this particular part, and you can also write this particular equation in this way, that is, we all know 0.7%, which is equivalent to 0.7 divided by 100. So this would be 0.07 times of ID. Okay, so you can also write this particular equation in this way. Okay, and the second thing is this, that is, just a second, the ID increases, drain current ID increases in just a second, drain current ID increases as the depletion layer or the junction barrier. So I'll write junction barrier only because in most of the book they had taken this particular term, that is junction barrier, as the junction barrier, just a second, as the junction barrier decreases. And the reason we had discussed earlier, that means obviously the electrons which were taking part in the formation of the depletion layer, they will now take part in the conduction, right? So therefore the ID increases as the junction barrier, as the width of the junction barrier decreases. Just a second, as the width of the junction barrier decreases. Just a second, let me move it over here so that I will get enough space to write this particular thing, that is width as the width of the junction barrier decreases. just a second, let me erase all of the things. As the width of the junction barrier decreases. Okay, and experimentally it has been seen that your current ID is proportional. I mean, the decrease in the current ID is proportional to 2.2 millivolts of 2.2 millivolts change in VGS. That means what? Let me first write this particular equation, that is ID del ID, the change in del ID, that means whatever the increment that will be happening in this particular drain current, it is proportional to 2.2 millivolts change in VGS. Okay, that means 2.2 millivolts, this is your VGS per degree Celsius. Okay, I hope you are getting this particular point. So to remove this particular sign, we know the formula of ID, that is equivalent to GM, okay, GM VGS, right? GM VGS, and your VGS is nothing but 2.2 millivolt time of 2.2 millivolt per degree Celsius. Okay, 2.2 millivolt per degree Celsius, and you can also write this particular equation in this way, that is 2.2 into 10 raised to minus 3 times of GM. Okay, I hope you are getting this particular one. Again, I am repeating, experimentally it has been seen that the increase in ID is proportional to 2.2 millivolt change in VGS. Okay, so that particular change, so basically this particular thing, that is 2.2 millivolt, it is nothing but, just a second, let me take different color first. Yeah, this particular change 2.2 millivolt, it is nothing but change in VGS. And if you could remember the formula we had studied in the previous section, that is your transconductance. If you could recall that particular formula, it was nothing but GM, it is equivalent to del ID by del VGS, right? So this is what is happening over here. So the change in ID, it is proportional to 2.2 millivolts change in VGS per degree Celsius. Okay, and when you try to equate with this particular formula, you end up getting this particular equation, that is 2.2 millivolts, 2.2 into 10 raised to minus 3 GM. Okay, so I really hope that you understood the entire concept and the entire thing that we had discussed in this particular concept of zero temperature drift. Okay, but still, if you have any doubt, if you are facing any difficulties anywhere, you make sure to ask me in the comment section. I will surely help you to explain that particular part there. Okay, so thank you for listening me patiently. I am ending this video over here. Thank you.